Hello there, Mr. Sutton here with the Pre-Cal Honors 4-7 Extra Practice #1 solutions on applications of exponential equations. For this problem, we want to know how long it takes an investment to grow to 142,000 if we're starting with 200, 12% annual interest compounded continuously. So the setup on this one, we're going to be using PERT, so f of t equals p times e to the rt. And in this case, we want to know how long. So we're solving for t, which means we have to fill in values for all the other unknowns. F of t, that's the target amount. That's going to be this 142,000. P, that's the principal. We're starting with 200. E is just E. R, well, 12% is the interest rate. So we're going to do 0.12 to actually plug that in for R. And then t is just going to be the only variable left over here. So in order to solve this, we isolate our exponential term, which is e. So we'll divide both sides by 200. That leaves us with, let's see, two of those zeros are going to cancel. It's basically going to be 710. I could probably do it on a calculator. I'm going to have to use the calculator at some point anyway, but that's 710. All right, so now to get the t out of the exponent, we have to take the log of both sides. For this one, I'm going to use ln because ln is log base e, so that's going to cancel out the e right away. So I'm going to have 0.12 t times the ln of e, which again, ln of e is just 1. So this is just 0.12 t equals ln of 710. And let me divide both sides now by 0.12. And at this point, it's up to the calculator. So all of that is going to come out to about, let's see, we'll say 71 or 7, depending on how much we want to round here. So 54.71 years. On this problem, we have the population of Kenya reaching 25 million people in 1990. We want to know when it reaches 50 million people with an annual rate of increase of 4.1%. So since this is just happening annually, we can just use the AB to the T formula, and we're trying to figure out when, so that's going to be the T value we're solving for, which means we have to plug in values for the other three unknowns. F of T, that's going to be the amount you end up with, so that's the 50 million people. A, that's what you're starting with, that's the 25 million. And then B, that's what you're multiplying by each year. Since we're increasing annually by 4.1%, that's going to be 1 plus 0.041. So 1.041 is going to be our B value. And then that's all being raised to the T power. So to solve for T, we have to isolate this exponential piece. I'll do that by dividing both sides by 25 to start off with. So that's a 2 on the left side there. And at this point, I've got no choice. I have to use logarithms. So I'm going to have log of 2 equals pop-out rule here, t log of 1.041. To get t, I just have to divide both sides by that log expression. So I've got log of 2 over log of 1.041, which I will now plug into the calculator. So plugging that in comes out to about 17.25, and that's going to be years. So there is actually a little bit more to do on this problem. They asked when. They didn't ask how long will it take. So it's possible that they want us to actually give them a year. If we're starting in 1990 and it's taking 17.25 years for this to happen, then this is going to happen at approximately 2007. On this one, Sutonium, yeah, that's a real element, has a half-life of 51 minutes. If there's 500 kilograms of the isotope now, how long does it take to decay to 2 kilograms? So since we're talking about half-life, and we have to wait a certain amount of time before multiplying by half, we're going to have to use the half-life formula. That's f of t equals ab to the t over k. So we're solving in this case for the t value. We want to know, again, how long. So that means we have to find values for the other 4 things that we don't know. So f of t, that's the target amount. That's how much you have left over, essentially. We want to know how long it takes to decay to 2 kilograms. So 2 is the f of t value here. A is what we're starting with. That would be the 500 kilograms we initially have. B, that's what we're multiplying by each time. Since this is a half-life problem, literally, we're multiplying by 1/2 whenever we multiply by anything. So this is 0.5 or 1/2, either way. T we don't know, that's what we're actually solving for. The k value is how long we have to wait before multiplying by 1/2. That would be the 51 minutes, so divided by 51 there. And at this point, we have to go ahead and solve for t. To start this off, I'm going to divide by 500 so I can get my exponential term by itself. So that's going to give me 1 over 250, or the decimal equivalent of that, whatever that is. And then I can solve for t by logging both sides. That'll pop this exponent out of exponent land. So I've got log of 1 over 250 on the left side equals, and now we pop out this t over 51 and have log of 0.5 on the right side. Next, to solve for t, I've got to do a little bit of algebra here. So I can multiply both sides by 51 to get that away from the t. So we still have a log of 1 over 250 getting multiplied by 51 over there. And I'm also going to have to divide by the log of 0.5, so that goes down below all of that stuff. And now it's up to the calculator. So making use of my calculator's fraction mode, that's the alpha y equals that gives you fraction stuff. Plugging all this in, it's going to come out to approximately 406.25, and that's in units of minutes. For this problem, we have a radioactive problem here. Radium-226 decays at a rate of 43.32% per 1,000 years. Current mass is 107.2 milligrams. How many years will the mass take to diminish to 11.3? Definitely a half-life kind of problem here. So it's going to be a little tricky setting up, but we know at least we're starting with f of t equals ab to the t over k. Now we have to start filling in some values. First off, we're asking in how many years. That's going to be the t value we're solving for, so we need numbers for everything else. F of t, that's how much is left over. That's the 11.3. A is what we're starting with, the 107.2. And then B is a little bit trickier. They didn't actually say the half-life was 1,000 years. They said it decays 43.32% per 1,000 years. So we're going to have to do a growth factor using 43.32% decrease, and that's going to happen once every 1,000 years. So our B value is going to be 1 minus whatever this is as a decimal. So let's see here. If I subtract 0.4332 from 1, let me do that on the calculator just to be careful here. So subtracting that on the calculator, my actual thing I'm multiplying by each time is 0.5668. So I'm essentially keeping 56.68% of the isotope each 1,000 years. And let's see, t, that's what I'm solving for, so I'll leave that as a variable in the exponent. K is my half-life, or it's my time I have to wait before I multiply by this number. That's 1,000 years, so we'll put 1,000 divided by 1,000 there for the k value. And let's go ahead and solve now. So I'm going to isolate the exponential term. We'll do that by dividing by 107.2. 11.3 over that is, well, whatever it is. I'm just going to leave it that way because I'm plugging it in the calculator anyway. Next, to get the exponent out of exponent land, I'm going to take the log of both sides. I've got log of all this stuff equals, and now I pop out the t over 1,000 and have the log of 0.5668 next to that. Now to isolate t, before I use the calculator, I'll multiply 1,000 by both sides, so that's 1,000 times log of all the stuff over here. And then down below, I'm going to have to divide both sides by log of 0.5668, so that's ending up down below when I move it to the other side. Now let's plug it in the calculator. All right, let's see what all this comes out to in how many years. And that's going to be a whole bunch of years, 3,962.83 years.